Hey everyone, in today's lesson we're going to continue learning about the dot product. This is almost like a part 2 of our previous lesson. I just thought it was too much to do in one. Today we're focusing on the dot product of algebraic vectors. So we're going to get right to it. So yesterday or last lesson we saw that for any two vectors, geometric vectors, a dotted with b was the size of a times the size of b times the cosine of the angle between them. Now, we know how to express vectors algebraically in the Cartesian plane. We do it this way with square brackets, and remember our components represent where that vector ends in the Cartesian plane. It starts at 0, 0, ends at whatever this point is. We're going to show that there's actually a nice tidy formula for doing the dot product. Because right now, if you have just two vectors a and b in the Cartesian plane, like just going off like this, if all you have is, I'll call that, like this, I'm just hypothetical. If all you have is where they end, it's not obvious what the angle between them is. You have to do some work to calculate their magnitudes. Is there a quick way to find the dot product? There is. I'm going to develop that with you guys right now. So remember that we can express any vector in terms of the unit vectors in R2. So vector A, I could rewrite as A1 times I hat plus A2 times J hat. And for B, I can write that as B1 I hat plus B2 times J hat. And so now let's look at the dot product of A and B using these guys. So A dot B is A1 I hat plus A2 J hat dotted with A2, A would be B1. Lots of A's and B's and I's and J's. Wait till we do 3 dimensions. So I'll just erase that. B1 I hat plus B2 times J hat. Now, in our previous lesson, we learned that the dot product obeys the distributive law and the associative property. So that means I can use FOIL basically, expand this out, and collect all the constants, the scalars at the front. So that would look like this. So from the first multiplication, I'd have A1, B1, and then I hat dotted with I hat. Then the outside guys, I would have plus A1, B2, I hat dotted with J hat. And then the inside guys, A2, B1, J hat dotted with I hat. And then from the last two, B1, B2, J hat dotted with J hat. Now you may be saying, well, that doesn't look very simple at all. But guys, remember, we had a property from yesterday, or our last lesson, that the magnitude, or the dot product of vector with itself is the magnitude squared. And I and j are unit vectors. So the magnitude is 1. And when you square that, you get 1. So I might just get a different color here to emphasize what's going on. I hat dotted with I hat is equal to 1 for this reason up here. J hat double J hat for the same reason is 1, right? Unit vectors. And we recall from the last lesson also that two perpendicular vectors, the dot product is 0. I hat and J hat are perpendicular. I dot J, 0. This whole term is gone. J dot I, this whole term is gone. And what you're left with is a super tidy little formula for the dot product of two algebraic vectors. A1, B1 plus that last one. You're probably panicking that I missed it. I caught it. That would be A2, B2 times J hat. Yeah, A2, B2. So this is neat. So this is a way to find the dot product between two vectors. if you have two algebraic vectors, to get the dot product, you multiply the x values together, plus you multiply the y values together. It's pretty cool, right? You do a1 times b1, the x values, and you add a2 times b2, the y values. Super quick, super easy, no need to draw things out, no need to find the angle between them. That's pretty cool that it works out that way. Just for fun, we're going to do a second proof. And this is the one time I do this a year, so we'll hopefully it goes well. We are going to use we're going to use the definition of the dot product, that A dotted with, or A dot B, I'll write it this way. Right, we learned that the other day. From the diagram, if you look at this diagram here, B plus C gives you A. If you think of vector addition, which means I can write vector C as A, minus B. I like to do this proof when I teach this because it's just kind of cool how the dot product falls out. Rearrange that would be A minus B. So we're going to use those two things. So, and again, the angles at C, this is the tail-to-tail angle between A and B. So forgetting about vectors, just what does the cosine law say? The cosine law says that the magnitude of that opposite side squared is equal to the magnitude of the other two sides squared added together, minus 2 times the product of those magnitudes times the cosine of the angle between them, which is theta. But look at that, AB cos theta. That's actually the definition of A dot B. The dot product definition falls out of the cosine law here. And if we do a bit of rearranging, so get the AB cos theta to the left, and I might, just to save some room, I'm going to emphasize in this lesson here that AB cos theta, we're going to replace with A dotted with B. So I'm going to move that to the left. I'm going to move C squared to the right and divide by 2. I'm going to do a few things at once here just to save room. So we get A dot B equals size of A squared plus size of B squared minus the size of C squared. And actually, just to save room, I'm just going to, that's 2 times the dot product. It's 2AB. So all I've done here is replace AB cos theta with A dot B and did some rearranging. Let's look at the right side and how that simplifies. So we learned when we talked about vectors in R2 that the magnitude of a Cartesian vector is the square root of its components, like Pythagorean theorem. So the size of A would be the root of A1 squared plus A2 squared, rooted, but when you square that, it would undo the root. And then you have plus B1 squared plus B2 squared minus, and then remember C is A minus B. So the x component of C would be A1 minus B1 squared, and the y component of C would be A2 minus B2 squared. So let's do some expanding here and see what kind of falls out. So we have all this stuff. B1 squared plus B2 squared. And right, this is just C1 squared plus C2 squared, right? Minus, okay, we'll have A1 squared minus 2A1B1 plus B1 squared. And then we'll have plus A2 squared minus 2A2B2 plus B2 squared. And we're almost done, actually. Check this out. We have A1 squared and another a1 squared, subtracting. a2 squared, we're subtracting this a2 squared. This b1 squared, we're subtracting it. This b2 squared, we're subtracting it. And all we're left with is we're going to be subtracting negative 2a1b1 and subtracting negative 2a2b2. And so what we end up getting is 2a1b1 plus 2a2b2. And remember the left-hand side here, this is still 2 times a dot b. And when you divide everything by 2, you get a dot with b equals a1b1 plus a2b2. Any way you slice it. So that proof was a little bit harder, but I think it's kind of cool how all that kind of ties together. The long and short of it is, this is the formula for the algebraic dot product. You don't need to use the definition for if you have two geometric vectors with the angle between them, you use this one. If you have two algebraic vectors where you have their coordinates, you use this one. So let's just do a couple examples, see how this works. I'll just leave that there. So for A, we're doing u dot v. So it's really simple. We take 5 and multiply by 4. We multiply the x values together, plus we multiply the y values together. And we get 20 minus 21, negative 1. The dot product of those two vectors u and v is just negative 1. How quick was that? We didn't have to find magnitude. We didn't have to find the angle between them. The formula works very well. For B, again, maybe you want to pause the video and try it and unpause when you're ready, or you can follow along with me here. So we have minus 2 times minus 1, multiply the x values together, plus 9 times 0. That's just 2 plus 0. That dot product is 2. Algebraic vectors are so nice to work with, and this is one reason. The dot product is super easy to calculate. So yeah, that's pretty cool. We did a question like this with geometric vectors, but it required us to know the dot product beforehand. Well, now we can calculate the angle between two vectors, two algebraic vectors, very quickly and efficiently. So if you recall, I'll just write this out. The way we did this the previous day when we were just working with geometric vectors is we took our dot product formula for geometric vectors and we rearranged it. And the last time I had to tell you what the dot product was. This time you can calculate it, right? So we can calculate all these things. So the dot product, multiply the x values, 3 times negative 2, plus multiply the y values, 4 times 7. On the bottom, magnitude of A is the root of its components squared added together, 3 squared plus 4 squared. And magnitude of B is negative 2 squared plus 7 squared. So that's negative 6 plus 28, so 22 on top. On the bottom, that's the root of 25, which is 5. And then 4 plus 49, the root of 53. So we can get that as a decimal and then do inverse cosine, or just punch that in and do cosine, inverse cosine right away. You guys know what you're about with respect to that. Divided by the root of 53 and shift cosine 52.8 degrees approximately. And what's really cool is that we didn't need to do any drawing, draw this out, reason out stuff. We could just actually use these tidy formulas. And the cool thing is we could program like a computer to do this, right? So thinking about 3D rendering and shading and shadows and whatnot. If you want to make a realistic shadow, you got to be thinking about angles and projections and all that. And you could program a computer to do these formulas and kind of figure out an angle to make a shadow at. Anyway, I'm kind of just rambling a bit, but all this stuff is so useful. But yeah, with these, we could program a computer to do this stuff. and that's really helpful to us. All right, I think the last thing we're going to do is we're going to prove the distributive law using the algebraic definition of the dot product. So we're going to do this by writing A, B, and C as their in terms of their basic components. So let us go ahead with that. So A dotted with B plus C. Okay, so A is the vector A1, A2. B plus C will be the vector B1 plus C1. Remember, you add their x values, and B2 plus C2. And now we'll use our formula we developed today. We're going to multiply the x values together. So we get A1, B1 plus C1, plus multiply the y values together, A2 times B2 plus C2. And now these are just all numbers at this point. We know numbers obey the distributive property, so that we'll get A1, B1 plus A1, C1 plus A2, B2 plus A2, C2. But again, these are all just numbers. So it doesn't matter what order we write this addition in, right? I could rearrange the order of addition. I could keep A1, B1 here, but flip-flop these two middle terms, plus A2, B2 plus A1, C1 plus A2, C2. And when you know it, that is the very definition of A dot B that we showed today. And the final part is the very definition of A dotted with C. We've proven it looks like an O, my apologies, but we've proven the distributive law using this algebraic formula. So pretty cool as well. All right, guys. So we've done a lot with the dot product, geometric vectors and algebraic, split over 2 lessons. I have some further practice for you guys from the 7.2 and the McGraw-Hill Ryerson text for you guys to try. In our next lesson, we'll look at some application of the dot product before looking at the second kind of product with vectors, the cross product of 2 vectors. Good luck. Stay well. Let me know if you need anything or any support. We'll talk to you guys soon.